Okay, so first of all, thank you for this invitation to this HSF meeting. So I give a brief overview of the Geant4 activities and also introduce maybe a discussion that will continue in the simulation session about the R&Ds. So I will cover three main topics. One is the Geant4 continuous mission, that is our daily work and daily deliveries. Then I will give some details about the next two coming release, that is the 10.7 release, which is coming in a few weeks, and some information about the next one next year that we plan to be a major release. And then I will enter the topic of how to cope with the high luminosity LHC challenges. So the Geant4 continuous mission are essentially three, I would say. The first thing is to respond to immediate experiment and user needs. So this response is about requirements on physics and functionalities. And we do that, that is the Geant4 collaboration make some work plans and listen to experiment and users, and we try to co-identify priorities for developments. And this response is also to support, that is, of course, everything which is about bug fixing or help about misunderstanding or whatever. The second mission is to improve the toolkit. This is a continuous mission too. That is the first item is to improve the physics modeling. That is improve intrinsically the models by improving their precision, but also provide alternative models to existing one when some other promising models are considerable. Then we think about improving computing performances, meaning that we try to make Geant4 faster. And we try also to reduce the memory footprint. And the last item is to enrich functionalities, and that is, I would say, in all directions. That is wider physics coverage, wider geometry functionalities, detector response, more user interfaces options, and processing and computing possibilities. And the last item, big item, is to anticipate needs and evolutions. That is the coming experiment challenges in that I would say also in all directions. That is energy frontier, intensity frontier, and we also keep watching at computing trends and hardware evolutions. So about the coming release. So in December, 4th of December, we'll have release 10.7. Let me give you some highlights. Probably one of the most relevant for this meeting is the introduction of a new tasking mechanism, which is provided this year under the form of a beta version. This tasking mechanism is there to replace today's multi-threading scheme we have. The interest of it is that it is a flexible mechanism, and is that it will offer opportunities for new functionalities, like, for example, the CB event parallelism that, for example, Alice is very interested in, which allows to split a big event on multiple threads instead of running a thread independently for each series of events. And one interesting thing also is that this tasking mechanism should allow an easier bridging with hybrid computing. That is, we may, with this mechanism, easily offload some computing tasks to GPUs, for example, and use GPUs as backend. There have been some quite some physics novelties in this release. One of the most interesting one is the charm and bottom hadron nucleus interaction physics, which is provided in physics list. Let me pick up some other items. One is in the electromagnetic physics with the new Coulomb scattering for E plus and minus, which with revised cross-section and using precise differential cross-section using parcel wave analysis. There have been quite effort also to diagnose the feed transport and quite development also to revise the feed classes, the classes for transportation in magnetic field, and it looks to be the source of quite improvement we observe. And we have also some effort to modernize the fast simulation classes and models, new scoring and plotting capabilities, and some effort also about configuration aspect, about the building Python module, and also start to have a more modular build of libraries. I mentioned some boosts. So apparently this year we got quite an interesting boost, which is still under measurement, but this is something which, of the order of 5 to 10%. And it looks that at first investigation, it looks that this is mainly coming from the improvement in the transport in magnetic field. For next year, 2021, we plan to have a major release. That is, we allow ourselves to break backward compatibilities, even if we will do our best to minimize this effort of the migration burden. Some of the motivation for this going to major release are the following one. This new tasking model I was speaking before will become the default one. And so it will become the default model to handle thread, which means that this will change the backend behavior of how these threads are handled, and it may change the API. The VecGeom solid geometry library will become the default also, and also which means that this changes the default behavior we have, and it also introduces an external dependency. We want also to move to C++17 as the minimum standard, which implies that we will drop some compiler support, so making also a non-backward compatibility. And this library, this big library, big work on library reorganization is also one of the motivation. The idea is that it will allow custom organization of libraries, and in particular, it will allow to split the big process library of Geant4, merge them, etc. So that will change library names and dependencies. So these are a set of reasons which convince ourselves that we have to move to a major release next year. Let's move now to how we see how to cope with the high luminosity LHC challenges. So this is the official timescale of the LHC upgrades that have been planned and are planned and are to come. I mentioned I mentioned where we are today. So the thing is well known, I guess, to many of you. That is luminosity increase, and for the Geant4, quite large luminosity increase, instantaneous luminosity increase, with about an order of magnitude more integrated luminosity. So, which is the challenges that everybody knows well. I would like to show that. I wanted to show that to compare, in fact, with the simulation R&D effort that we had and we have in Geant4, just to give the time scale, the comparative time scale of these efforts. So, in one of the major evolution of Geant4 was the adoption of the multi-threading, and this is something which has been adopted at the beginning of 2014. That is, since 2014, this multi-threading capability has been merged to the production, and so is in production since 2014. And you see, it took about 5 years for this effort to be completed. And you see, this is a quite significant time if we compare to the LHC plans. You know well also the Geant4 R&D effort, which has been made for about 6 years and which end in 2019. So again, you see a quite long time to lead an R&D effort. So we are here today, and here this is basically where the data taking will start. For sure, it doesn't mean that the new softwares have to be already at that time, even if it will be much desirable. and certainly some software evolution will still continue during the data taking period, but it gives already the time scale of what is still in front of us to conduct the evolution that are requested to cope with the high luminosities. So in fact, we don't have much time, I would say, to cope with these challenges. So to cope with these challenges, there are three lines which I understand we almost agree on that. That is, these are the three main lines that we find in Geant4 or in the HSF. So the first one is to continue with the adiabatic improvement of the detailed simulations. This starts with the technical improvement, that is the code revision, move to modern standard, use more acceleration techniques when possible. And for example, in Geant4, this was made during the Geant4 work. You have this, for example, this tessellated solid who are using a vectorization technique to handle facets in much more quicker way. So even if we are still in a scalar transport mode, it doesn't mean we can't use any of these acceleration techniques, and some of them can be used in Geant4 today already. This technical improvement must come with the physics precision improvement. Typically, the thing is that if you have some speed up factor by f, and if you want to keep the systematic uncertainties not growing faster than the statistical one, it means that typically you have to reduce at the same time the uncertainties. That is, you have to improve your precision by typically a factor square root of f, simply to scale with the statistic that this boost factor gives you. So this is something which we have to keep in mind. So when you deal with the electromagnetic physics, and some of the electromagnetic physics models can go to very high energies, it's less obvious with the hadronic models, where most of them are based on phenomenological models, which needs to be tuned, which needs to be revised, and getting more precision in this case is not that easy. And in fact, if you are satisfied with a level of precision today with the present version, it means that if you go to 10 more, if you want to be 10 times faster, you need also at the same time to have your precision, which is about 3 times better. About the speed up factor, this is not excluded, but I insist this is not promised, that a factor about 2 is reachable in a few years. I just would like to remind the factor we have today, which is a good one, about 5 to 10% speed up in the incoming next release. So if we conduct still good effort of revising our software and improving it, it's not excluded that we can reach some sizable factor on the regular simulation. The other item is to improve fast simulation. Still continue working and improving the classical parametric approaches, that is with typically the well-known G-flash for electromagnetic showers, but also invest on modern techniques using machine learning. And this machine learning could be a way to approach to more difficult shower parameterization, for example, like the hadronic ones. So these are things we would like to continue, and that we would like to continue interacting with the HSF and experiment for that. The thing we'd like to point is that, which is well known, is that these developments are important because this fast simulation may be the sort of security net of that era, LHA era, if we are not able to speed up enough the regular simulation. So the fast simulation may be this sort of security net of that era. And the last item, which is the most ambitious one, maybe, are the R&D on accelerator and new architectures. So there is the large spread of GPUs which is coming these days. The question is, how much could there be a solution to simulation needs? and we have a slide after on these GPUs. We have quite concern with the GPUs in the simulation, and we think that this can be a high reward, but also at high risk. And the thing is that we are not convinced today that GPUs could be the solution for the full simulation. And maybe there could be also a partial solution to the problem. And then the question would be how to articulate efficiently GPUs and CPUs simulation in an efficient flow. So this is a very difficult question. Another thing we have to do to continue is to benchmark of promising architecture. And here we are very much interested in benchmarking this A64 FX ASIC. So these are a list of questions about concern we have with GPUs. That is, porting the software to porting simulation to GPU is not simply a question of computing power. We know that GPUs have very strong computing power, but this is not only that question, because this is also related to very much how the processing flow is organized. What is the processing flow model, and if you fit to that or not. So GPUs, I would say, are kind of made for what I would call laminar flows. That is something which is quite regular. But the particle transport is way more turbulent, and it's way more turbulent because of the stochastic nature of the physics which is simulated. By that, I mean that the processing flow is permanently interrupted by decisions which are made on the basis of random numbers. We spend all our time to decide what to do, if random X, if random Y, if random Z. So in fact, these decisions are part of the flow itself. That is, we constantly make decisions, unpredictable decisions on the basis of random numbers because of the Monte Carlo nature of the physics. So these are several consequences. And for example, the population of particles vary drastically in number and types during a simulation. And so if you start with a model with one particle per GPU thread, then rapidly you got a thread divergence. So you may be aware that people in medical, for example, have successfully implemented electromagnetic simulations on GPUs, but you may know also that this is at rather low energy, and for which you have only a few particles, and in a domain where, in fact, you don't have much of these divergence problems. But in high energy, the picture is completely different. And you see that, in fact, in high energy, we have something which is far different from the sort of constant flow of the same rays that is the problem in image rendering, and which was, in fact, the origin of these graphical processing units. GPUs also are meant for calculable problems. That is, you have a lot of arithmetic units which are provided, but in Geant4 we have many processes which are not calculable. And this is the case for many processes, and we are using large table of cross-section in final states instead. And this is very much the case, for example, for all this low energy neutron transport, where you have all these very shaky cross-sections, and all that comes from table. You don't have way to compute that efficiently on the fly. But it is also the case for intermediate energy. That is when you are doing Bertini cascade or these sort of things. That is all these things which are non-calculable easily. We use also quite many data here, but this is also the case if you are interested at low energy transport with detail of atomic structures. So all these things makes that what you need, in fact, are frequent memory access to large memory portions. So this makes also something which is uneasy to fit with GPUs. So with this challenge in here, we believe that it makes difficult to anticipate if a viable solution will be identified. So we don't say that there is no solution. We say it will be at least extremely difficult to have a full simulation. So maybe a partial solution. So this case of these issues here are also quite similar to the one you face with vectorized transport. So it doesn't mean we don't have to do nothing on that, certainly not. So what is the strategy for the R&D? We see essentially two main axes. The first one is to invest on learning on various hardware. So, and these hardware are, of course, the GPUs, but also this A65X, for example, and whatever would come. This is to educate ourselves. This is to understand the opportunities and understand the limitations, and also understand where we should invest more. You will hear today about efforts to prototype project, to prototype the electromagnetic simulation on GPUs. And this sort of attempt is a key activity because with the doubts I expressed just before, we really need to know where we will land in this GPU fields, where we will land in terms of performances. So this is really important to see where what sort of performances we will get with this simulation, knowing that for the electromagnetic physics is chosen because it is calculable. So it does not face off all these memory accesses I was speaking before. So this sort of activity, I would say, is essentially the mandate of the Geant4 R&D task force. So again, this is a very key activity we have to pursue. The second aspect, I would say, is a bit more a blackboard one. That is, we have to study the Paris nature and to study the Paris potential in the particle transport problem itself. That is, if I show you a plot here on the right, you have here a shower development, a 100 MeV electron shower development, which is something you may not be familiar with. But in fact, so what is represented in green are photons, in blue electrons, and in red are positrons. And these thin and thick lines are consecutive steps in time, CPU time. So here you have the CPU times, and here you have the particle number when it is created. So if you start with an electron, then it is making...
Mark, if you are running out of time.
Oh, sorry. So yes, I'm just finishing. So you have this alternance of steps here. And for example, if, you have here, let's say, a positron, which is created, and then you have these two gammas, which are the two gammas daughters. And this sort of processing would be the fastest possible processing in terms of mother-to-daughter relations. So this would be in a machine where you would have an infinite number of cores and where you would start the tracking of each secondary particle as soon as it is created. So in this way, it will be the fastest possible processing while taking into account the mother-to-daughter relationships. Today, with the scalar transport, what you have is that you put all these lines one after the other, and so you have this scalar processing. Any parallelization thing will sit between this scheme and the scalar one. So the question we would like to answer is, what is the parallelized potential in the transport problem itself? And the other question is how to fit this parallelized potential into the existing parallelized solutions. And then what again we could expect, what cost in terms of memory, how many tracks we should need to have to keep in memory, what would be the memory traffic, this sort of things. And we believe that this sort of issue will be faced by any project which will start to handle parallelism with the particle transport. So this will be for ourselves, of course, but also for external people who would be interested to define solutions, or for the young generation, and also, and last but not least, to help finding new ideas and to emerge. So, and again, for that, we will need exchange between the Geant4 and HSF expertise. This will be a key aspect to make progress on that. So thank you for this invitation.
Okay, so I think we can give, thank you, Marc, and I think we can give the field for questions.
I see a hand raised by Chris Jones.
Yes, thank you. Can you hear me?
Yes.
So I wanted to know, what are the opportunities for the experiments to give feedback on the new task model, since the previous threading model wasn't a perfect fit for what many of the experiments are doing now?
So this for 10.7, the tasking model will be optional, but it will be available to anyone who wants to use it. So we expect the experiment to have the freedom to give us feedback on what has been implemented.
I see Marco Catania raising his hand.
Yeah, my question is not directly to this talk. It's more to the fact that we are somehow faced by, I don't know if it's political or financial decisions to go towards putting the bulk of our computing on HPCs, where GPU is essentially ubiquitous. So, I mean, what do we do if we fail to work in this direction with Geant4?
So yes, one thing is that Geant4 did not make the decision of buying HPCs.
Not clear. That's the problem.
Yeah, that's a problem. I think at least I see two options. The first option is the fast simulation. That is, it is our security net. Of course, it will be not optimal, not the best thing we could imagine, but at least it should allow experiments to run. So this is one thing. And if we fail with the GPUs, the one other opportunity to explore, I would say, is this sort of ARM technology with this A64FX. And I would say it is of course, we'll do our best to see if we can run with GPUs. But if we can't, and if at some point we are able to demonstrate that we can or we can't, I would say we not invent from scratch the computing power. So at some point there will be, we may face the point that we could only say sorry, but we can't use GPUs. But for that we have to demonstrate things. So yeah. So the backup solution for me are fast simulations and explore other possibilities, other platforms.
Andrea, you want to ask a question?
Yeah, just a quick question related to what you said actually about the A64FX, I mean, ARM. What is the status there? I mean, does the software actually run on ARM and on this particular platform? I mean, when you say that you're very interested in benchmarking, I think we all would be very interested. I mean, have you started this already?
That is, we have just started discussion. That is, we have colleagues in Japan who have expressed some interest also. And so we are just starting discussion to see if and how we could have access. And for now, this is really too soon to say whatever, but at least there is strong interest.
So it would be on Fugaku actually directly on the supercomputer in Japan.
Luckily, yes. Luckily.
Okay. Thanks. Very interesting.
Not sure, but luckily.
Okay, maybe we take last two questions from the Google document. Maybe Gloria, you want to maybe choose one of your 4 questions and ask it?
Yes, maybe I stay on fast simulations, and that to me are very much tied to specific detector technologies. And there is a lot that is being done in the experiments about it. So how do you see the interaction and the role of Geant4 in this?
So I would say that I would count primarily on the HSF to make these exchanges as good as possible and join Geant4 on that. That is, for me, the first stage is really the HSF, which is in its mandate, I would say, in its spirit, is really meant to make better communication between experiments. And of course, Geant4 will be more happy to join about that. And if we can import things which have been developed in a way generic enough, then we'll be import to that in Geant4. We have also some activities about fast simulation in Geant4 still, which is ongoing. So this is really a matter of I would say putting the right people in the same room, essentially. And I would count much on the HSF to help with that.
Okay, maybe we take last question from the live notes. Graham, would you like to ask yours?
Yeah, thanks. So I was wondering about the tasking framework. It's quite interesting development. And do you think this will allow Geant4 to like batch the work a little bit better between the different threads that we understand would probably improve the cache usage on CPU? So process all the electrons which are in flight at the same time, for instance.
That's a good question. I'm not sure. I would probably push the question to Jonathan Madsen, who has been developing that. I'm not completely sure it will be that easy, but at least this is a flexible model. And I don't know, maybe it could, but
yeah, I can comment.
Yeah, okay.
Jonathan, if you want to comment first, go ahead.
Oh, I was just going to say that there's no real way to say, hey, have this task run on this specific thread. So as far as organizing, you know, all the electrons to run on one particular thread, that's not really enabled by tasking.
Yeah, and at least at this moment, each individual event goes to a single thread. So it's not far different from unthreading. And in the future, we have sub-event parallelism, but it does not necessarily mean we merge all the secondaries back to the master or whatever, and we sort and send only the electron to a particular thread. That is most likely will not happen, because the communication between master and the worker thread will be too dense.
Okay.
Yeah, thanks.
Thank you. I think